Okay, so you had the opportunity to see the list of contents. So let me begin. Oh. But the page, strona nie chce przeskoczyć. Co ja mam? Też nie przeskakuje. Tu jest page up, page down. Okay. So let me first define apparent horizons. So imagine a space-time that contains a singularity. For example, a universe model that collapses to the big crunch, to the final singularity. And suppose there is an observer O who flashes at time t0 a bundle of light rays in all directions. And suppose the bundle is initially diverging. When the bundle is coming near to the final singularity, it will start to reconverge, or so everybody believes, but you will see from what will follow that it's not necessarily so. And the locus where the bundle has zero divergence is a two-dimensional surface. Let's denote it by ST for a moment. And its location in space-time depends on the moment of emission of the bundle and of the location of the source of light at this time t0. So suppose the observer O follows a world line in space-time and flashes such a bundle of light at every instant before hitting the final singularity. So the collection of all those surfaces ST corresponding to all the times before the final singularity is a three-dimensional hypersurface H in space-time. Now, this is not quite in agreement with the original definition, but by Hawking and Ellis, but well, with a slight abuse of the terminology, I will refer to H as the apparent horizon of the observer O. Okay, so that was the definition, and now the motivation, why I started this research that I discuss now. In the Friedman models, each comoving observer has a differently located apparent horizon. I will show pictures in a moment. The model that is used in the pictures in the next slide, this is spatially flat Friedman model, has the metric written here. And well, the scale factor S is proportional to the TBC, this is the moment of final singularity, minus the time coordinate in the power 2/3. And well, its mass content of this model is dust with such density. Okay, so these are the pictures that illustrate where the apparent horizon is. This is the left picture is in comoving coordinates. This is the present time, the lower horizontal line. The upper horizontal line is the final singularity. This is the observer O in the center, and it's the profile of the observer's light cone at this moment. This is this pair of curved lines, and the apparent horizon of this observer, it's this second pair of curves. Okay, the curves marked with crosses is a profile of the light cone with the origin at some other point. At a point on this first light cone.
You say that if you draw a picture of all other light cones, then the zero divergence surface is left green, right?
Green and brown, yes. Okay, the right picture is the same, but in different coordinates. Yeah, the horizontal coordinate here is r times the scale factor, and this is the angular diameter distance from the observer. So in this in these variables, the big crunch is a single point. And here we see very well the radius of the light cone at any given time. Well, it's really the geometrical size of the light cone. So it shrinks to 0 at the final singularity. The apparent horizon is the pair of straight lines here. And here we can distinctly see that at the apparent horizon, the size of the light cone begins to decrease. And for comparison, there are two other light cones with a vertex here and with a vertex here, so that you can see how it looks. Okay, these thin curves that converge at the big crunch are the word lines of particles of the cosmic medium. In the left figure, they would be vertical straight lines. And such a structure exists around every comoving observer word line in any collapsing Friedman model. If the model is somewhat more sophisticated than this, but still with Robertson-Walker geometry, then okay, some slight deformations may occur, but qualitatively it's the same picture. Now, by contrast, in the Lemaitre-Tolman models, the apparent horizon in earlier papers has been considered only for bundles of rays emitted at the center of symmetry. I will define the Lemaitre-Tolman model in a moment, and we will tell you a few words about its properties. So in this case, the apparent horizon can be defined in two ways. One way is to say that the apparent horizon is the locus where the surface areas of the light fronts emitted from common points achieve maxima. So at the same locus, the radius of the light front achieves a maximum. Or the second method, as the locus where the expansion scalar of such a bundle becomes 0. K is the tangent vector field to the rays. And both these definitions determine the same hypersurface R equal to 2m. Well, it will become clear in a moment what this formula means. So this is one exemplary space-time diagram of an exemplary Lemaitre-Tolman model that expands from a Big Bang and evolves toward a final singularity after a finite time. So this is the future apparent horizon. This is the past apparent horizon. Well, why this hypersurface has any meaning will become clear in a moment. Oh, and the mass function is used here as the radial coordinate. Okay, so it was puzzling. Well, that was the apparent horizon of the center of symmetry, but it was puzzling where the apparent horizon would be for a non-central observer. So this is the question that I asked myself, and a paper was born in this way. It's published in Reports on Mathematical Physics. And I will present, in this talk, I will present the contents of that paper. Okay, so here I will show, in this talk, I will show where are the extrema of the radii of the light cones and the loci of the zero expansion of light bundles for such rays that were emitted at non-central events. And in this case, the three sets listed here are all different, quite unlike in Friedman model, namely the locus of maxima of R, the locus where the expansion of the rays is 0, and the locus of R equal to m. Okay, now the loci of theta being 0 and of extrema of the area distance from the observer, they do coincide. But if O is not at the center of symmetry, then this area distance from the observer is not equal to the function r in the model. And the extrema don't coincide. Okay, so now let me define the Lemaitre-Tolman models. So suppose we assume that the space-time is spherically symmetric, but not spatially homogeneous, like in Friedman models. It's just spherically symmetric around a single word line. So from the Killing equations, one can conclude that the most general spherically symmetric metric has such a form. C, A, and R are unknown functions of the coordinates TR, and that they should be determined from the Einstein equations. And the Lemaitre-Tolman model is the solution of Einstein's equations for this metric with zero pressure and this function big R being really dependent on the coordinate small r. And after the Einstein equations are solved, this metric here emerges. E is an arbitrary function of small r. It appears as an integration constant during solving the equations, and the function big R is determined by this equation here. Well, you can see it's really an ordinary differential equation with the integration constants being not constant but functions of the coordinate r. Lambda is the cosmological constant. Now m is a second arbitrary function, and this is the formula here for mass density. So this solution was first found by Lemaitre in 1933 and then discussed by Tolman and Bondi. It's called most frequently Lemaitre-Tolman-Bondi, less frequently Lemaitre-Tolman, and these additional names are added only to avoid confusion with the Friedman-Lemaitre models, because otherwise the credit for the discovery of this solution belongs to Lemaitre alone. Well, the bad luck of Lemaitre was that he used to publish his papers in a journal that nobody ever reads. So this paper remained unnoticed for a long time. Tolman knew about Lemaitre and he published his paper in a more famous journal. So that's why for quite a long time, the solution was called Tolman model, but this was a great injustice done to Lemaitre. Okay. You can also explain how it happened that in GRG these papers are published. Okay, in the GRG journal, there was a series of papers called Golden Oldies. These were reprints of important old papers, when necessary, translated from other languages to English, well, with comments by today's specialists. And yeah, Lemaitre was number 2 in this series. No, not inventor. The idea came from Alan Held, who was the editor-in-chief for a long time, and I just picked up the idea and continued for some 15 years. The same Brussels paper had also the Lemaitre with the expansion of the universe. The same journal, but not the same paper. Not the same paper, but the same journal. Yes. Yes. Okay, so the properties and astronomical implications of the Lemaitre-Tolman model were discussed in, well, considerably more than 100 publications, and this number is still increasing. Now, when the function E is negative and lambda is equal to 0, then the solution of this equation here can be parametrically represented in this way. And there is one more arbitrary function here that appears as an integration constant. And this is the Big Bang time. And as you can see, the singularities that occur at eta equal to 0 and eta equal to 2 pi are in general at a different time for each shell of constant r. Now, these two formulae here, the formula for the metric and the equation defining big R, they don't change under arbitrary transformations of the coordinate R. So we can choose the coordinate R as is convenient, and here in the stock it will be convenient to choose the function m as the radial coordinate.
Right.
Yeah, in those ranges where it's not constant. Now, when it's constant, well, actually with constant R, this is simply the Schwarzschild solution. So, okay, but M can have extrema, but I don't want to get into those details. Now, the Friedman models are the limiting case of this Lemaitre-Tolman solution. Here it's written, the definition of this limiting case. So to appeal to your imagination, you can imagine the Friedman models as in the left figure. The expansion of each matter shell is rigidly defined by its radius. Yes, in the Lemaitre-Tolman model, the velocity of expansion and the radius of the shell are completely independent. And okay, here the initial explosion is all at the same time in the comoving coordinates. Here it's not. Okay, now let me tell you some words about the light rays in a Lemaitre-Tolman model. So here are the geodesic equations for this metric. I will not discuss them in any detail. K is the tangent vector field to the geodesic, and lambda is the affine parameter. Because of spherical symmetry, the last two equations have first integrals that are written here. J0 and C are constants. And with this...
J is angular momentum.
Yes.
And C, what?
C is 0 for radial rays. So when C is not 0, this is a measure of how much non-radial the ray is. Now, with these equations, the conditions for a geodesic to be null becomes this one here. Okay, well, now when C is equal 0, then J0 and K theta are necessarily 0. And when theta is different from 0 or pi, then K phi must be equal to 0, and then the geodesic is radial. Now, these two coordinates can be adapted to any single geodesic in such a way that the geodesic stays always in the hypersurface of theta equal to pi half in the new coordinates. But this hypersurface is in general not flat. Okay, and for the pictures that I will show you later, the geodesic equations were integrated numerically. Now let's discuss the extremum of the function R. This green label is somewhat disturbing. Let me try again. Maybe it's better here. Okay, so the function R has extrema along light rays in places defined by this equation here. So on future directed curves, KT must be positive. So when the model is collapsing, this quantity is negative. And when shell crossings and necks are absent, then this derivative must be non-zero everywhere. So solutions of this equation in a collapsing model exist only when this product here is positive. And on a null geodesic, this equation, after using this one here, assumes such a form. And then from the equation of evolution, with lambda equal to 0, we obtain the following equation defining extrema of R along a light ray. Okay, I will here is this equation. So you can see that when r is smaller than 2m, then both terms in this equation are non-negative. So this equation may hold in this region only when both terms are 0. Now this case will not happen in what follows, so I don't want to discuss it, but there are some interesting details hidden here. Now, in all other places, 1 plus 2e must be positive in order for the metric to have the right signature. Okay, this is the metric. 1 plus 2e must be positive. Okay, RT is negative in a collapsing model. So from this equation, we can see that the solution of this equation can be r equal to m only on radial geodesics, with c equal to be 0. Now, when c is different from 0, this equation has solutions only where r is greater than 2m. And after some manipulations using the geodesic equations, we can find such an equation for the second derivative of r by the affine parameter. Now, from the formula for mass density here, we can see that mr times r by r must be positive. So the first term in this equation here is always non-positive. And the second term is negative only where r is smaller than 3m. So when r is smaller or equal to 3m, then this second derivative is negative, and this r extremum, if it exists, must be a maximum. Now, where r is greater than 3m, both minima and maxima are possible. Now, for radial geodesics with c equal to 0, the second derivative is always negative, so only maxima can exist on radial geodesics. Okay, so now let's discuss this in an exemplary explicit Lemaitre-Tolman model, which is given in the following way. The Big Bang function as a function of m is this here. The big crunch function is this. Well, it's not important. The values of the parameters are not important. They were necessary to draw the pictures. And, well, this you saw this pair of equations already. So when I write this equation, the solution at the final singularity, we obtain from it the following explicit formula for the energy function. So you see it's negative, so the model is recollapsing, but it's spatially infinite because m has the range from 0 to infinity. And this, when m goes to infinity, you see e goes to 0, so m over 2e goes to infinity too, so r goes to infinity. So this model has infinite size, but at infinity it becomes spatially flat. Well, it's a fictitious model. It's not a model of any physical object, but it proved useful for several theoretical considerations before. So that's why I used here. So you could see this picture already before. These are the profiles of the Big Bang, Big Crunch, r equal to m and r equal 3m. And the right picture are contours of constant big R written into this frame. And the contour of r equal to 0 consists of the Big Bang, of the line m equal to 0. This is the center of symmetry, and of the final singularity. And the subspace theta equal to pi½ of this model can be imagined by rotating this diagram here around this axis. Okay, and in this model, I will now explicitly find the locus of extrema of R along bundles of future directed rays emitted from the observer, where the line, well, the source will be somewhere here. And the rays in the figures will all be in the theta equal to pi half hypersurface. There will be 16 emission points, and at each emission point there will be 512 rays emitted in regularly spaced directions all around. Rays number 0 and 256 are radial, all others are non-radial. Okay, and so this is the graph of the points of maxima of R for this combination of rays that I told you about a moment ago. On rays that go off with in the direction of decreasing R coordinates, there are no maxima. On other rays, there are maxima but no minima. And this is the image obtained by projecting all those points along the world lines of the cosmic dust on a surface of constant time. And here on the second picture, you can see that as predicted, all the maxima are greater or equal to 2m.
Wait a minute, the second picture, what is in the second?
Sorry?
What is in the second picture?
It's the MT diagram. This is the M coordinate horizontally. This is the time coordinate. So it's in the it's a projection in the direction orthogonal to the left picture. Okay, and these are the projections of this, well, because this is a kind of contour map of a surface in a three-dimensional space. So this is the projection on a surface of constant time. Now this is okay, the left picture will be a projection in this direction here on this surface here, and the right picture will be a projection on this surface here. Okay, so that might help you imagine the how this surface looks in space. We consider the rays running only in the theta equal to pi half hypersurface, but each bundle of rays emitted from a fixed initial point consists of sub-bundles, and each of those sub-bundles is in such a hypersurface, but in a surface of constant different theta. They are connected to each other by rotation about a point. So the complete projection of the whole set of our maxima on a three-dimensional space of constant t can be imagined by rotating this figure around the phi equals 0 semi-axis. Okay, so in this direction. Now, the situation gets more complicated when the emitter is placed closer to the center of symmetry. Then some rays that go off with decreasing R pass near the center of symmetry, and on those rays, R goes through a minimum and then through a maximum. So the next figure shows the extrema of R along rays that are emitted closer to the symmetry axis. Okay, so the dotted lines are loci of R minima, and the continuous lines are places where R has extrema. And these contours undergo an interesting evolution as time progresses. Namely, for the earliest emitted bundle, the maxima and the minima, this ring number 1, they are separate rings. But as the time progresses, these two contours come nearer to each other. This is contour number 2 of maxima and contour number 2 of minima. And at a certain time, they touch each other. And for later times, they separate in orthogonal directions, so that at later times, the contours are still consist of two separate loops, but each loop contains both minima and maxima. Okay, between on rays emitted between the smaller loops at later times, R decreases monotonically. Okay, this is the view. Okay, this is the view direction in the next figure, and this is how this surface looks when projected. Okay, the horizontal axis is still m, and the vertical axis is now time. Now, this graph is an illustration of what I said before. This is the TM diagram, and dots here show maxima of R, crosses show minima. So as I told you, well, this green curve here is R equal to m. This blue curve is R equal 3m. So as I told you, the maxima are all between 2m and 3m, and the minima are all at R greater than 3m. Okay, I showed you the locations of the maxima and minima, but I didn't show you the locations of the rays in space-time. So this left figure here is the projection of the light rays of on a surface of constant t. As you can see, they behave completely differently than in a Friedman model. Yeah, this is the this cross here. This is the location of the emitter. In a Friedman model, there in this projection, they would all be straight lines going out of this point. Sorry, this is the emitter here. This is the emitter location. This is the center of symmetry. And here, as you can see, they bend over and approach the big crunch tangentially to the contours of constant R. So there is the transition from this model to the Friedman model is discontinuous. Okay, these are the large dots are R maxima. These crosses are R minima. This is the green circle is the R equal to m on ray 0. And well, okay, I will explain what this line of small dots is. I will explain later. Okay, and this is the view, a three-dimensional view. Let me go back one page. Okay, this arrow here shows the view direction in the next figure. So this is the three-dimensional view on the family of rays. These large dots are the locations of maxima, and this is the full ring of R maxima. Okay, and the endpoints of all the rays are at the big crunch. The surface of the big crunch is inside the surface of R equal to m, close to it, but inside, and it has a similar shape. Okay, so this was about the R maxima. Now, let's discuss this set of where the expansion scalar of the family of light rays becomes 0, first in a general Lemaitre-Tolman model. So, well, after some manipulation, this is the equation of this is the formula for the expansion scalar. So on radial rays, C is equal to 0, and this whole second line disappears. And you can see that on radial rays, the locations of theta equal to 0 are the same as the locations of maxima of R. They coincide and both are at R equal to m. Now, on non-radial rays, this term being 0 is in general not a solution of the equation theta equal to 0. So they are different. Now, this derivative here, it goes across the bundle. So to calculate this quantity numerically, you need two light rays, the main ray G1 and G2, a nearby ray that goes off the same initial point but in a slightly different direction. And this must be calculated at constant t. So for each point on G1, we find a corresponding point on G2 with the same t. Yes, and at that second point, R is equal to R2, KR is equal to K2. And then this is the approximate formula for this derivative, approximate numerical formula. Now, all other quantities in this equation are intrinsic to a single geodesic. And, well, it may happen, for instance, it happens at the point of origin, that R2 is equal to R1, but K2 is different from K1. So at the point of origin, the expansion, scalar of expansion is infinite. But at other points, theta may go to plus or minus infinity and may jump between plus and minus infinity. So it can be calculated from this formula that a real jump, well, it may be a numerical artifact, but if the jump is real, then it may be only from minus infinity to plus infinity. If you are interested why, then it's a simple homework for you. And this is reasonable because the jump from minus infinity to plus infinity means that the bundle of rays was focused to a caustic, and then on the other side of the caustic it disperses again. Yeah, how it could happen from plus to minus infinity is hard to imagine. Now let's discuss the location of this set of theta equal to 0 in the same explicit Lemaitre-Tolman model that I discussed previously. So the emitter positions will be the same as for the R maxima, but the number of emitted ray bundles will be smaller to make the pictures clearer, and the number of rays in each bundle will be still 512. So these are the locations of theta equal to 0 on rays emitted, well, from this place here. Well, it's a complicated picture, but each contour consists of, well, on most rays, theta goes through 0 twice. First, the first zeros are locations of first zeros are marked by F, of second zero by S. So this is the numbers correspond to different emission points. So for emission point 1, this is the contour of first zeros, this brown one, and the contour of second zeros for the same point is somewhere here. And the upper ends of all those contours are in space-times, they are near to the final singularity. Now, on rays that are emitted in directions contained between these two structures, theta has no zeros. Okay, this is the less is not important. This is the view on the neighborhood where the arch of first zeros goes into the arch of the second zeros. Okay, this is the first emission point, first zero. Yeah, between those two arcs, there is a ray on which theta has a single zero.
You get some
well, yes. Well, this is supposed to be a contour map of some surface in a three-dimensional space, but it's complicated. So, okay, here are projections of the same contours on different. Okay, this is simply a repetition of the earlier figure. This here, the upper picture, is a view from the right side. From the right side, and only the 5 non-negative have. Okay, so on this part on contour number 5. Okay, so this small thing here is part of this blob, and this larger thing is this branch here. And this lower picture is the view from below. Okay, it's not very readable, I'm afraid. Okay, and these are the graphs of theta as a function of time along some selected rays for the earliest emitted bundle. Numbers are labels of the rays. So on the outward radial ray, which is number 0, theta begins at plus infinity and then decreases monotonously to minus infinity at the contact of with the big crunch. It has only 1 0 along the way. And on all non-radial rays, theta goes to plus infinity at the final singularity. So the bundles approach the final singularity while diverging. And this is not what the Penrose-Hawking theorems would have us expect. Okay, and on those rays, okay, there is one ray here that on which theta has a single 0, and there are rays on which theta has no zeros, but you can see it starts with at plus infinity, it ends also at plus infinity. Okay, and this figure here shows the time ordering of various events along the rays on the earliest emitted bundle. So this is the location of the time coordinate of the maximum of R. This is the location of R equal to M. This is the location, the green curves are the locations of the first 0 of theta, and the blue curves are the locations of the second 0 of theta, and the gray dotted lines is the big crunch. So here you can see distinctly that the locus of the second theta, 0 of theta, approaches the big crunch when the ray direction approaches radial. And you can see that these time orderings change from ray to ray. Okay, here, for instance, the first 0 of theta occurs earlier than R equal to M. And here on these rays, it occurs earlier. This has some consequences, and I will tell you what they are in a moment. Okay, for rays emitted closer to the center, here at this point, the picture is still more complicated because on some rays passing near the center of symmetry, the theta may have up to 6 zeros. So I will not show those pictures. They are in the paper, but they are too complicated to show here. And now I'm coming to conclusions. Okay, so the locus of theta equal to 0 may lie earlier than R equal to M and then maximum of R, depending on the initial direction of the ray. Now here you can see that the maximum of R is always earlier than the first 0 of theta, but that's big only at this location. At some other locations, theta equal to 0 may lie earlier, but I did not show these figures. So at a point where theta equal to 0 occurs earlier than 2m, well, from the point where theta is equal to 0, you can still send an outward radial ray that will go some distance toward larger R. Now, points where R equal to M is earlier than theta equals 0, well, those points on those rays became isolated from larger R before theta became 0. So you can see that for non-central observers, this hypersurface R equal to M rather than theta equal to 0 is a one-way membrane. Okay, and this locus of maximum R is always earlier than R equal to M. So points between them are not yet isolated from the communication with the region of larger R. And now, where are the trapped surfaces? So in this graph, they lie between the zeros of theta. Yeah? They lie where theta is negative. So for instance, you should focus your attention on this light blue ray here. It has first theta equal to 0 here, second 0 here, and all along this ray between those zeros, the expansion is negative, but if you follow this ray further into the future, theta becomes positive again, which means that the surface intersected by this ray would become untrapped at later times. Okay, I told you this, that the rays have infinite divergence at the contact with the big crunch. Convergence occurs only on the radial rays. So the formation of a trapped surface is not the unique signature of a black hole in the making. Yeah? Where theta becomes negative, some communications with the outward lying region is still possible. So this hypersurface R equal to 2m still has a universal meaning in a collapsing Lemaitre-Tolman model. It signifies the presence of a black hole inside it. Now, this meaning of R equal to m was identified by Barnes and Sekeres by considering spherical trapped surfaces surrounding the center of symmetry. So events in the region R smaller than 2m are cut off from communication with R greater than 2m in a Lemaitre-Tolman state. Yes, and the transition from Lemaitre-Tolman to Friedman is discontinuous in one more way, namely the individual apparent horizons in the Friedman limit for non-central observers appear abruptly. Yeah, they don't really exist before taking the limit. Okay, so this is all I wanted to say.
Thank you very much.
May I have a question?
Well, it's not clear to me because what follows, well, this is all a result of calculations. So what follows from here is looks to be in contradiction to Penrose said. Yeah.
What assumption is different from here than from the assumptions that Penrose?
Well, this is an explicit model, so the assumption is only the only assumptions are the Einstein equations, spherical symmetry, and dust source.
They have assumptions.
Yes, I know, but I can't really answer this question because, you know, the definition of apparent horizon by in the book by Hawking and Ellis, it's really a tower of definitions and it's difficult to follow. So,
and it's not what Penrose and Hawking used in a sense. That's not identical to the definition that Hawking and Ellis used.
Yes.
That's not identical.
Yes, yes. They defined trapped surfaces by families of light rays going off from a surface. And here I was considering light rays going off from a point. So, yeah.
May I have a question?
That's from the, okay, yes.
If you don't mind, I would have two questions, okay?
But you are not very clearly audible. Can you speak louder or maybe take off your mask? Or?
Yes, I would have two questions. Can you hear that?
Yeah.
Can you hear me, Andrzej?
Oh, okay, we're getting technical help.
Okay, can you hear me?
Yes, now we can hear you, yes.
Perfect. I would have two questions, if you don't mind.
Yes.
First one, suppose that we wish to model our universe by Lemaitre Tolman, okay? And what would be observables of horizons, just to measure?
Observables of what?
Horizons.
Well, the definition of the horizon is such that you cannot see anything that is on the other side. So, yeah.
Okay. So maybe I will ask you a second question. Does Lemaitre Tolman model with naked singularity have any apparent horizon?
Well, if the singularity is naked, then the horizon shouldn't exist.
Yes, but so somehow this equation that to determine horizons should somehow be not applicable. Yes. Suppose that I wish to determine theoretically, somehow properties of naked singularity. So somehow I should find that equations to determine horizons, don't work.
Yes. The equation determining the horizon should have no solutions in such a case.
Okay. So can I just suppose that I wish to deal with Lemaitre Tolman with naked singularity? Suppose that I wish to quantize that model. Okay. So so can I completely ignore existence of horizons, or I should somehow can you hear me?
Yes, I can hear you, but I'm not sure I understand.
Okay. Suppose that I wish to deal with Lemaitre Tolman, but with naked singularity, okay?
Yes.
So can I, at that moment, completely ignore horizons, possible, because, can I completely ignore horizons at that moment?
Well, if the horizon doesn't exist, then of course you can ignore it.
Yeah, but I would say, but you should first prove that somehow equations, to determine horizons are not applicable.
In every case that you will consider, you should first verify whether the horizon exists or not. And
that's what I'm saying. So is there any tool to do that?
Say it again, please.
I mean, do we have any tools to examine whether we have horizons or not?
Well, I showed you the equation defining the location of zero theta. That's one possible definition of the horizon. So you should verify whether this equation has solutions. If not, then the horizon doesn't exist.
Because you must know that there is someone called Pankaj Joshi, who he's very much excited with examination of Lemaitre Tolman with naked singularities, and he's even trying to to find it, to have some indications, in observation data. That's what I mean. That's what I wanted to ask you. Okay, thanks.
Some other questions? If not, thank you again.
Thank you.